The factor theorem. We're going to start with the proof of the factor theorem, which you're not likely to be ever asked to reproduce. Now remember, the factor theorem is a special case of the remainder theorem. It's the case when the remainder is 0. You know that something is a factor if the remainder on division is 0. Let p of x be a polynomial such that p of some value c is equal to 0. Then x minus c is a factor of p of x. Conversely, or in the reverse direction, if x minus c is a factor of p of x, then p of c is equal to 0. So we have the proof for the forward direction. We know from the remainder theorem that when we divide by x minus c, we can always write p of x in the form x minus c times the quotient of x plus the remainder. We looked at several examples producing expressions like this. Since p of c is equal to 0, because remember in this direction we're saying p of c is equal to 0, it follows that r must be 0. So p of x is equal to x minus c q of x. We don't bother writing down the r because it's 0. And therefore, because it's x minus c multiplied by q of x, that means that x minus c is a factor of p of x. So now we're going to look at the backward direction. And the backward direction is where we know that x minus c is a factor of p of x. If x minus c is a factor of p of x, then by definition, the remainder when p of x is divided by x minus c would be 0. By the remainder theorem, this is equal to p of c. Hence, p of c is equal to 0. Remember, when you divide by some x minus a, for example, a linear factor, we know that the remainder is equal to p of a, and that's all we're saying here. We know that the remainder is equal to p of c, and the remainder is 0.